to continue the quantum machine learning, especially how to improve the noise robustness on the current device. So just a reminder, last time we mentioned how to construct the whole quantum machine learning pipeline from the encoding to the architecture and also to training the parameters. So this time we also follow the similar structure. So we'll finish several TQ examples first, and then we're going to introduce how to do the state preparation, like encode the classical information to the quantum domain, how to do that with high efficiency and also robustness. And thirdly, we're going to introduce how to search for the architecture. So just like the previous lectures, we introduced the neural architecture search, right? So for the quantum, we also have architecture search for the quantum structures. So and then finally, we're going to introduce one recent work that is on how to train the parameters with high robustness. Okay, so let's firstly continue some TQ examples. So just maybe a quick reminder for the TQ is a library that we implement in the PyTorch, and we can use that to do the quantum operations. For example, how to do the matrix modification between the state and also the unitary matrix. So we implement some of the key operations. For example, we can use the TQ quantum device to instantiate a quantum device with 5 qubits, and also we can import the functional. So remember, in the PyTorch, sometimes we import torch.functional as f. So here we can use the torch quantum.functional as TQF to make sure we can use all the gates. For example, if we want to use the Hadamard gates to implement the entangled operation between the 0 and 1 state, we can just directly use tqf.h and apply this device to this input arguments. And also, we implement some other ways to apply this gate, because if we are using Qiskit, maybe some physicists are using Qiskit, and the syntax is a little bit different, so they are more familiar with using like instantiation of a gate directly and then apply this gate to the device. So it's just like using the large uppercase of H, so you can create a new object for the H class. Okay, so for some other usage, we also support different ways to apply the gates. I'm going to not skip these details, but you can check the documents for TQ to how to use those different kinds of gates, including the rotation gates with some parameters. And just have a quick look of the data structure we are using in the TQ. So basically, all the states are implemented with the torch data structure. For example, torch.zeros, you can use that as the tensor for the length of the 2 to the power of n. Remember that we have the exponentially large of the state vector to represent the state, and we need to make sure the initial number is 1, or sometimes you want to use, say, a magnitude encoding. You can initialize the state as the state you want. And later on, we'll introduce how to prepare the state on the real device. And for some other operations, like the C0 operation, we also implement that with the state structure, this matrix in the TQ in torch tensor format. And also, again, for some other properties, the first is dynamic commutation graph, which means after you apply this gate, for example, you apply this H gate, you can print the state. You can find that the state is actually changed, because after you're calling this line of code, the state will be different from the previous one. So it's just like a dynamic graph. After you're calling this operation, all the states will be changed, instead of a static graph that you construct graph and then do the compilation optimizations. That is the way that in some other frameworks like Qiskit or the TensorFlow Quantum. And also, we support the batch mode. The batch mode means that, so says in some learning task, we want to process the image for a large batch, and then update the parameters and compute the gradients and update parameters together. So in that case, we can also specify the batch size in the quantum state. For example, the Q state here is you can pass argument to specify the BSC here, which is 64. That means you can instantiate 64 different states, and then you can encode the actual quantum image to these states. And also, we of course have the GPU support, because we implement all the operations in TQ in PyTorch, so we can directly send the state to the GPU, and all the later operations will be accelerated by the GPU. And finally, we have this automatic gradient computation. So which means, say, if you want to update some of the parameters, right? So say I want to update the parameters of some gates or some other operations, and then we can compute the loss here. So here we are showing that the loss for a state preparation. So that is this this operation, and then we can compute the loss. So this loss is in the TQ's is in torch data structure, and then we can very conveniently directly call the loss.backward to compute the gradients on all the parameters in the circuit. And we also support a different encoding method, for example, the amplitude encoder, the phase encoder to do arbitrary encoding for your different classical data or the quantum data. So we also have these converters to different other frameworks like Qiskit. You can just import the plugin here, and then you can specify the TQ to Qiskit and use this quantum model, and then you can also draw the result for that. So in terms of the speed, we compared it with the previous other frameworks, for example, the Pennyline, which is developed by another company called Xanadu. And actually, because they don't have support for this batch mode processing and also the GPUs for processing, so we can achieve a much higher speed up compared with the Pennyline in blue, and we have this in brown. And the speed up is even larger when we have large number of qubits. And also for the large number of layers, we can see because more layers for the Pennyline, we have to do that sequentially with low parallelism. But for the TQ here, we can have a very small increase of the runtime compared with the Pennyline here. So using the TQ, overall, you can leverage the power of the existing GPU frameworks to accelerate all the simulations. So that would be much faster than the other frameworks. Okay, so that is the framework. So how can we use this framework to do some actual tasks? For example, as we mentioned, there are 3 stages in the QML process. One is to prepare the state. So you have an image, you want to encode the image to the quantum state. And the second is to design the structure of the parameterized circuit. And then you want to train the parameters in the parameterized quantum circuit. And the first step is to do some state preparation. So that means you have a classical image. And how can you encode this image to the quantum state? So the quantum state preparation is actually widely used not only in the quantum machine learning, say the amplitude encoding in the QML, or in some other tasks, for example, solving the PDE equation. You also need to initialize the quantum state with the system's initial state. And also for some other error correction code, for example, some color code or surface code, you also have specialized structure for all the qubits initial state. So state preparation here is actually, if you have a very good start of the fidelity of the state, you can expect better fidelity for the later operations on the qubits. So there are several very previous works to develop those decomposition-based preparation. So for example, here we can see typically the number of gates we have to use, especially the 2-qubit gates, is required is 2 to the power of n, which means, say, you have 6 qubits, and then you want to prepare the arbitrary state of that, you need to use 2 to the power of 6 number of qubits. So that means to faithfully cover all the space, you have to use a large number of 2-qubit gates. So we can see for the 6 qubits, 12 or 20 qubits here, the number of 2-qubit gates is actually increasing. And also here we can compare our method of the variational state preparation versus some other baseline decomposition-based method. So we can see if we are using the variational ones, which means you have some parameters in the circuit to prepare the state, then the usage of the 2-qubit gates will be much smaller than the other baselines. For example, these two in the blue and also in yellow, those are the preparation with the fixed decompositions. So during the say after we prepare or using some arithmetic decomposition of the initial state, we have this quantum sequence of gate to prepare the state. But when we actually run this circuit on the actual device, we can see a very severe drop of the accuracy because of during the decomposition of the states, we don't consider any of the noise on the actual device. So here is a simple example. So say if we want to prepare a state of qubits with number of say 5 or 6, and in the green curve, we can see that is the noise-free simulation of our state preparation, and we can see that actually the fidelity is very close to 1. But after we run this, say we just want to, given a quantum device, we want to run this series of gates to obtain an initial state. And in that case, we can see only with 4 qubits or 5 qubits, the fidelity of the state preparation on real device will be very low. So say if we are using 6 qubits, the state preparation circuit itself will just cause the fidelity to very close to 0. So because of the large number of gates and also number of layers, so it makes the very high reliable state preparation very challenging. So there are several previous works on how to do this state preparation. So for example, on one dimension, there are 2 different kinds of method. One is the noise unaware preparation, which means you just prepare all the states on the noise-free simulator, and then you can deploy on a real device. And then another one is to use the noise-aware method. So say you can say prepare the parameters or the circuit structure with some noisy simulator that captures some part of the noise on real device. And also you can use the real quantum machine to directly train the parameters, as last time we introduced the parameter shift or some other ways to better capture the actual noise, right? So another dimension is that you can use the gradient-free based method or the gradient-based. So gradient-free, say the evolutionary research or the genetic algorithm or some Bayesian optimizations, those are gradient-free method to update the parameters in the circuit to prepare the state. So we can see that is one way. Another is gradient-based. So using gradient-based method, you can obtain gradients with parameter shift, or you can just do some backpropagation. So we can see those 2 dimensions they have a grid. And for the first dimension, if we are training parameters with noise, then you can have better robustness because you are aware of the noise of the real device. And if we are doing the training with the gradients, for example, using parameter shift or backpropagation, the training efficiency will be better. So imagine that if we are training a large, say, neural networks, and if we're not able to do the backpropagation, but only do the zero-order optimizer, then that will be very inefficient. So in that case, there are 2 dimensions, and there are several previous works trying to do, say, backpropagation on noiseless, noise-free simulator to do the or some training with the actual device, but not using any gradients. So we try to achieve something that is the best of both worlds, right? So how can we have this high noise awareness, and also how can we have this better training efficiency? So in that case, we have several recipes to achieve this goal. So the first one is that we need to find some gradient proxy, because the gradient evaluation and the computation process is pretty costly. And also during the construction of the circuit or of the variational parameterized quantum circuit, we need to consider to use the native pulse level operations, or we also have to design those hardware efficient ansatz or the structure of the circuit. So ansatz here means like how many layers of the circuit and what kind of gates you want to use, and also the positions of each gate to use. So let's firstly have a look at the gradient proxy. So the gradient proxy means that, say, if we are running this circuit on the real device, and then the circuit will be impacted by the real noise, right? And then if we obtain the result from this device execution, for example, we run the circuit, and then we can obtain the real quantum density matrix from the circuit, right? And then we can run another simulation in parallel with the real execution of the circuit. So say there are 4 layers here, and then I can run the classical simulator for 4 layers. And then I can also obtain a density matrix from the simulation. So that's 2 parallel processes. One is actual device running, another is the simulation, right? But the simulation doesn't have any noise, but the real device execution is impacted by the noise, right? And then for the training process, we can replace the simulated density matrix with the actual real device matrix. So in that case, when we do the backpropagation, we can use a straight-through estimator here to replace the simulation density matrix with the actual quantum device run density matrix. So this result will be impacted by noise. And then we can use this method, this result, to do all the way back propagation through the simulation. So the reason behind that is, say, for the actual device, we are not able to obtain any intermediate result, right? Because we are running on a real device, and because of the non-cloning theorem, we cannot clone some of the qubits out and see what is the state. So the only way we have access to the noise impact result is to actually run that on a real device. But we still want to have a high training efficiency using some gradients. So in that case, we still need to use the intermediate result. And the intermediate result will be provided by the simulation result. But only the final result is from the actual quantum device. So we have this noise impacted density matrix, and then we just back propagate the noisy density matrix through this simulation. So in that case, we can achieve this noise awareness because the final final density matrix is noisy. But also we can achieve the back propagation because we have all the states in a classical simulator. So we can achieve the higher reliability and also better training efficiency together. So you may ask whether using this estimated gradient is very accurate or not, because we can see the previous layers, they actually don't have any noise, and we directly use the noisy result at the end, whether that will cause some problem. So we compare this estimation of the gradient versus the most accurate result, which is using the parameter shift rule to run for each of the parameter. So just remember, like last time we introduced parameter shift, and for each parameter, you need to run the circuit for twice and obtain the gradients for that single parameter. So we compare, that will be the most accurate one, but that's also very costly because you have, say, 100 parameters, you need to run 200 times of the execution. But for our method, we just need to run once of the actual device running, and then all the parameters can be gradients can be obtained simultaneously. And we can compare this estimated gradients proxy with the actual parameter shift rule gradients. And we can see that after we compare the cosine similarity between those two results, we can see as we continue training, the cosine similarity is pretty high. It's always like higher than 0.9. And that means, like, using this method, we can have a very accurate and also very efficient proxy estimation of the most accurate gradients. So another thing is that we also need to use the hardware efficient on-site structure design. So the hardware efficient means that for different topology, so say for on the actual device, we have different connectivities between the qubits. Say we can have a linear connection between the qubits, just 0, 1, 2, 3. And we can have a ring connection, right? So 0, 1, 2, 3, and then there should be a connection back to 0. And also sometimes for other more complicated, they have say a heavy hexagon, like you have a hexagon connection, and also you have qubits on each of the edges, and sometimes you have a grid connection. So in order to achieve a high efficiency, we sometimes have to design the topology aware on-site, which means all the gates, or especially 2-qubit gates, they are just lie on those connections. Say for these linear ones, we have gates between 0 and 1, 1 and 2, and 2 and 3, but there is no gate between 0 and 3 directly, because in that case, we have to pay for the extra cost of the swap gates to finish the execution. And also for some other ring connections or some other different topology here, we also have to design the structure or the on-site that is respecting the connectivity graph of the actual device. Another thing is that we can directly scale the pulse magnitude according to the parameter. So remember last time we introduced how we do the control of the actual each of the gate. So for example, the control pulse here on the qubit 0, you just have a very Gaussian pulse here, but actually that one is similar to Gaussian, which is called a drag pulse here. And then during the actual execution of the rotation x, say the x is rotation x for 180 degree. And if we just want to rotate for a smaller degree or some other numbers, we can actually change the magnitude from a very large one to a smaller one, because the rotation angle will be in proportion to the area and the curve of this pulse signal. So in that case, we don't have to do the previous compilation where if you have Rx here, you may decompose that to multiple gates. But here we just directly tune the shape of the pulse, and then we can reduce the overall duration of the program. And also that's also the case for the controlled gates, like 2-qubit gates. Like say the C0 here, that's actually the 2 CR gates. And then we can also change the duration besides the magnitude. We can see the duration here right now is pretty long, but we can reduce the duration to a shorter one or increase that to a longer one, adapting to the actual parameter we want to use. So for evaluation here, we are using several different states. So especially for quantum machine learning state, we introduced previously, if we want to encode this classical image to the actual device, we can see, say, if we are reducing the dimension of this image to 4x4, so that should be 16 values. And then we can use just 4 qubits to encode all the pixel values. And then we can see the state here should be those different numbers, say 0.048, or the largest one will be 0.41. And those numbers will be representing the classical values of the pixels of this image. And also, we also have some other different states as evaluation. Say for the PD state, sometimes they are a sign function here. And also for the arbitrary state, we sometimes have both a real component and also the imaginary component in our arbitrary state. So the first thing of our method is that we can achieve a reduction of the coherent errors. So just imagine that we want to execute a rotation gate of 40 degrees. And on the actual device, there is always, for some reason, there is always a over rotation. So say I send a signal of I want to execute a 40-degree rotation, but on the real device, it's always executing 40 plus 10. Like I achieve a 50-degree of the rotation. So what should we do at this time? So the way we want to do is that we just send a 30-degree of the rotation, because we know that there's some unknown reason, unknown control imperfection that can increase the rotation angle by 10 degrees. So if we want to do 40, and then we just send the 30-degree to device, and then the final result will be 40-degree rotation. So that's also the case here. We are seeing that the reduction of errors, because we are especially coherent error, is because those over rotation and also under rotation. So after we train this angles according to the actual real device feedback. So say I see the feedback is always 10 degrees larger, and then I can just reduce the signal I send to the device, and we can see the reduction of the error after we train longer epochs. And also compare with some other method. For example, just using the parameter shift, like all the result will be all the parameters will be running for twice. We can see compare with that our performance is increasing faster than the real machine parameter shift, or using some gradient-free method to do the training. So that indicates a higher training efficiency using this proxy gradients. And also we want to compare with imagine like a arithmetic decomposition method, and also coupled with the subree. The subree is introduced in the first lecture, where we do the forward mapping and reverse mapping, right? So that's the default mapping method for the current Qiskit framework. So we can compare this arithmetic decomposition in Qiskit or using the Matonal decomposition. So those ones are not using any parameterized gates, or they are directly decompose the mathematical equation of the state to a series of gates. So we can compare our result on the actual device with this with the Matonal decomposition or the Qiskit, and we can see that the fidelity of the gradient proxy is actually higher than the Matonal or Qiskit results. And also compare with some other device, like on the IBM Geneva or some other Hanrui Lagos device, we can see the robust state method. The gradient proxy can also achieve the highest fidelity. And also with other, remember the grid of different ways to train the parameters, we can also achieve a better accuracy compared with those, say, noise unaware search, or a noise unaware parameter shift, or some gradient-free training method. So one very interesting phenomenon we find during this training process is that whether we should use the pulse level changing of the gates or we just use the gate level decomposition. So we can see at the first stage, the red curve here is the pulse level onset, and the green here is the gate level. So at the first several steps, we can see the pulse level onset is worse than the gate level. So the reason is that if we are decomposing to the gate level, all of the gates are already well calibrated by the say IBM team, and they have a very high efficiency and also high fidelity. So if we are doing the pulse level onset, we at the first stage we change the values, and then that will introduce some of the additional errors. But after that, after we train for a large number of steps, we can see that actually finally the pulse level onset will outperform the gate level. So that is because all the errors we introduced can also be later reduced by the gradient aware training. So in that case, because pulse level onset will have a shorter duration, so we can see the final performance will still be better than the gate level performance. Okay, so that's for the training of the encoding of the state for the initial state, right? So after that, we also need to decide what is kind of the circuit structure, like the architecture, to say how many gates we want to use, and what kind of the basis operation we want to use, and also what are the locations of those gates. So here we are introducing a very robust and also scalable circuit architecture search method. So this is also like for general parameterized circuit with different kinds of rotation angles and also the different gates. And we are targeting those variational quantum algorithms, for example, the VQE or the quantum neural nets or some quantum approximate optimization algorithms. So just the first challenge for the PQC, we already see that the large gap between the actual noise-free simulation and also the measured result on the actual device. So we can see it's not always better to increase the size of the circuit, because when we increase the circuit size, we also increase larger noise. So at some point, the benefit of introducing larger circuit size, for example, the larger learning capacity, is neutralized by the noise introduced by those additional gates. So in that case, we can see a sweet spot between the very small number of gates versus very large number of gates. So you can see we have to carefully design the size to make sure we are at around this sweet spot, which achieving the larger best accuracy on the actual device. So another challenge is a large design space. So as we said, because you can tune the parameters. So in that case, many of the different architecture can achieve the similar task. For example, here we can use some U3 rotation gates or some X gate plus some CZ gates, right? So those different gates sometimes can achieve a similar task because you have the freedom to train the parameters with regard to your task. And also, how many number of gates is also is flexible. For example, you can just use one block of this gates, or we can concate this circuit for many different layers. So that depends on how large is learning capacity you want to use. So just last lecture, we introduced more blocks of the gates will have a better expressivity, right? And also for the position of the gates, say if we just decide how many number of gates and also what are the gates type. For example, we just want to use 4 U3 and then 4 CU3. And we also have many different choices to place those gates. Say maybe we want to use the C3 CU3 first and then other U3 gates. Maybe we just have this structured way to place those gates. So that's also the flexibility here. So the goal of our framework of the quantum NAS is that we want to automatically search for a best architecture across this large design space. And also we want to make sure the search process is aware of the actual quantum noise. So the automation and also efficiency is achieved that we can do some parameter sharing between the different candidates in the design space, because this is kind of a two-level optimization. So we have one level of the circuit structure, and then we have another level of the parameters in the circuit. So our goal is that we just want to find the best structure giving a device. And then after finding this structure, we can use the structure for any task we want to use. So in that case, we don't have to train each of the candidates in the design space. Otherwise, we have to pay the training cost for, say, 1,000 times, because there are a large number of different circuit candidate structures in the design space. So we're proposing some parameter sharing to just train once, and then we can use that for many different candidates. And also another thing for the noise robustness is we can do the feedback using the actual device. So say we have 1,000 of the candidates, and then we can evaluate each of them with the actual device, and then we can see which one performs best on the actual device, and then we can use that for the other tasks with good generalization ability. So another thing is that we do some co-design across the stack. So say after we have the circuit structure, maybe if we do the different compilation process, like say assigning different physical qubits, that will also lead to different performance. So in the classical computing, you don't have to worry about this, because say you design a model, and then you can use arbitrary, say H100 or A100, or just your laptop. You will expect that result will be the same. But on the actual quantum device, it's not the case. After you design this program, you also need to be very careful about which qubits you want to use, because even with the same structure on different qubits, the performance will be different because of the different noise level of different qubits. So for the first parameter sharing process, we are using a circuit that is called a super circuit. That means, say you have a large design space, and for this design space, here we give a simple example. Say in this design space, I want to have a choices to select arbitrary number of the subset in this design space, because you can always construct a large enough of design space that encompass all the possible gates in the structure, right? So for example, we can have this block for many layers, and then you can select arbitrary subset from that design space, and maybe some of them is very good for the target device, maybe some of others are not good. So our goal is to find the structure here. It's not to train the parameter, but just find the good structure, and then we can use this structure to do any arbitrary task, and the parameters will be specialized for the task, but for the structure, that is the circuit structure, that is specialized for the device. So our goal here is just to find the different which structure is the best given this design space and also given this device. So in that case, here, the one circuit that contains all the possible gates in the design space, we call this a super circuit, because it's sort of all the ensemble of all the different sub-circuit candidates. So we call it a super circuit. And then the reason why we are using the super circuit is, as we mentioned, so if we say, if we want to understand like which one is the best for a device, we have to make sure the parameters are already there, right? So in that case, a naive way is that we just train those three, say giving a given task, and then we just train those three parameters, and then evaluate on real device to see, oh, this one is 10%, that one is 20, that one is 90, and then maybe that one is best. But we have to do the training for parameters, and that has a large cost. So maybe we just need to find a way to train the parameters just for once, and then use that for all the candidates. So that's how our motivation behind the super circuit parameter sharing. And we have this a strong assumption behind that is that is, say, with the shared parameters, the previous, the best one, this one, say, that should be 90%. And with the shared parameter, that one should also be the best. Maybe using the shared parameter is not as good as 90%. Maybe this is 5%, and then that one is 70%. But we are still using this to find the best one, and our goal is achieved, right? So in that case, we need to have assumption that if we're using this inherit shared parameter from super circuit, we can also those good sub-circuit is also the good ones with the train from scratch circuit, right? So in that case, later on we'll show the empirical result that whether this assumption hold or not. So, but during the training step, we want to make sure this assumption is like have a good order preserving among those different sub-circuit. So in that case, we are proposing some specialized training process. So that means first one is called front sampling. Another is called restrict sampling. So that means during the training process, we are actually doing some sample of the sub-circuit. For one step, we do the sampling, and then we update the parameters in that sample. And then for the next step, we find another sampling, right? So here we are showing an animation for the training process. So as the first step, we can have maybe all the circuit here, and then during the training, each step we can find a different sub circuit. For example, this one only contains 4 gates. This one also contains 4 in the block N, and then we only update the subsite. So for next one is a different sub circuit, and then we update different subset of the parameters, right? So in that case, we have a sort of a make sure that all the different candidates in the design space, they are trained to a similar level. Maybe they are all only like half as good as the training from scratch, but that's already good enough. We just need to make sure that they are order preserving and let us to find the best one. Then that's all. So in that case, we can do this sampling and training process. And also we propose some sampling small techniques to make sure the sampling is not too drastically different between those 2 steps. So the first is that we just do the front sampling, which means for some layer, say if we are just want to sample 2 gates in the first layer, and then we always select the first 2 gates. And also for this block, if we are doing sampling, say 3 gates, we just select the first 3 here. So we sort of shrink the sampling design space a little bit to make sure the sample process is smooth enough. Another thing is we restrict the difference between 2 consecutive steps. So maybe first step we sample the 3 gates first and 2 gates second layer and 4 3. In that case, after if we are doing another step of sampling, say sample this one, and there are 5 different layers, and we maybe reject that because there are too many layers different from the previous step, and that may make the training step very unstable. But maybe we can have a threshold. Maybe 3 layers is the largest number of alternating different layers between 2 steps, right? And then we can see if we are doing a sampling with another step, and we find that there are only 3 layers different from the previous one, and then we can accept this. So the intuition is that during 2 consecutive steps, we just want to minimize the difference, right? So in that case, the training will always have a pretty nearby trajectory on the whole landscape. So that is called the restricted sampling of the super circuit training process. And next step, if we are finding that there are only 2 layers, then we can just accept this step. So here is just a intuitive illustration of the values here. So say the first step we are sampling those 4 gates, and those 2 result in 2 values in red means that we are changing the parameters according to the training data. And those for other white values, we'll just freeze those, right? We don't use them, and also we don't change them. And also for next step, if we're sampling the first 3, we are changing those values. But the 1.1, because it's not sampled in those 2 steps, we just keep the previous value. And for this one, it's not sampled again, and we still keep this. But for this one, it is trained for 3 steps, right? And for other ones, we just keep the previous value if that is not sampled. So that means the training process is actually continuous in terms of the parameters and values. So remember that we have assumption for the order preserving property of the weight sharing super circuit versus a super circuit trained from scratch. So we want to make sure the order preserving property is good enough that we find the best one with this proxy is still the best one with the ground truth, right? So here we are showing some result with the performance, and x-axis here is the super circuit sub-circuit performance with the inherent parameters from the super circuit, and the y-axis here is the performance with the weight with the train from scratch parameters. So that's the y-axis value will be the ground truth, and x-axis value will be the efficient proxy. So say if we want to find the best one, say the one that has the largest value here, and then we can see this one, this value with the proxy will be the best one, and then that one corresponds to still the best one. So in that case, we can just use the very cost-efficient proxy to find the best value. So we don't have to pay the cost for each of the individual training. So then we can just take this, and then for the later other task, we can generalize this search structure for other different tasks. So during the training process, we can also have another, we also co-design this sub-circuit with this qubit mapping on the target device. So the qubit mapping means that how can we map the algorithm qubits to the actual device qubits. So say this is the topology of the IBM Q Yorktown machine, and we have 5 different qubits. And sometimes if you are doing a bad mapping to that qubits, we need to pay additional cost of adding swap gates to those different qubits to make sure they can execute the desired gates. So here we are doing some evolutionary search of this circuit structure and qubit mapping. So because we already have the previous super circuit to very efficiently evaluate all the candidates, so what we have to do is only to one way is that you just check all the performance on all candidates, because you already have the parameters from the super circuit. You can do that, but if you want to run that on the actual device, then that's also very costly. Even if you don't have to train parameters, you still need to run each of them on real device. So say in the design space, sometimes you have say 10 to the power of 10 different candidates. Yeah, how can you run that many of times on actual device, right? So in that case, we still need to use some very cost efficient and sample efficient search engine to search in this design space. And in that case, we are using the evolutionary search. So evolutionary search engine will co-search the sub-circuit structure and also the qubit mapping. So say this structure is coupled with the mapping between this algorithm qubits to the green one, and maybe this second one is mapped to the blue one, and third one is mapped to the red one, right? So we can have a vector to represent what is the qubit mapping of those 4 algorithm qubits to the actual device qubit, and also what is the structure. So say for this first layer we have 2, second layer we have 3. So we can use some called a gene, like gene to like just a vector to represent the design for in the design space. So we can use the gene to do some mutation, crossover. Later we'll introduce that. But the idea is that we can use this evolutionary search with the gene here, and then we can update the population in the engine according to the performance from the actual device. The performance will be evaluated on the actual device, and then we use that to update the population inside search engine. So not sure if I'm familiar with the evolution search, but the basic idea is that we have the gene here to represent what is the current status of the candidates. And maybe say we have this different number of layers, we can use some numbers to represent the structure. And then we have the first way to do the exploration of the space is to do mutation, which means we can just change some of the elements in the gene, right? So we can change the first to 3, and we can also do some crossover, which means say maybe we have a parents like candidates in the population, and we want to generate some more child population. We can do a crossover, which means we take some gene from the first parent, and then second parent, we can create a new one as the child of those 2. So that's a crossover process to generate the new exploration of the space. So after this crossover and mutation, we generate a new population, and then we evaluate, we get the feedback, and then we generate a new population. So in that case, after many iterations, we can find a very good small population of the good circuit structure and also the good qubit mapping. Okay, so in that case, we say we already find the best one here, just using this structure and also this qubit mapping, right? And then we can just fix this one. And for any task, say I want to use this circuit to do some training of the to use this circuit for the quantum machine learning task, we can just use this and then train the parameters according to your image classification task. Or some other times we want to use this for the quantum chemistry, we can still reuse this structure because we already find this structure very suitable for a device. And the insight for the suitability here is sometimes it's because of the small, say maybe these 2 qubits have a very lower error rate, and then we can put more learning capacity on those 2 qubits because you can afford more gates on those 2 qubits. And for some other bad qubits, we just have a smaller depth of circuit. So that's the structure will be very tailored for the target device you want to run the program. So during the so after that, if you want to do some specific task, we can do a final round of the parameter training. So the final round will be just train those parameters according to our previous introduced, say, parameter shift or some other ways to update the parameters according to our task. So that's already like after we find the higher level structure, we can do the parameter training according to our target problem to solve. So during this process, we have another very fine-grained way to reduce the noise, which is the pruning of the gates. So this is very intuitive, which is that, say, for some during the training, the parameter will change, right? Just like the pruning of the neural net's weight. So if the sum of the value is very close to 0, and then the mathematical formation for that matrix is just identity gate, right? Identity gate, you don't have to do that because that is not changing any state. So we just remove this gate with values very close to 0, and also of course very close to 2 pi, because sometimes there are some like cycle between those, like the values, say a rotation gate plus 2 pi, that's the same as the previous one. And also during the training, we can find some threshold to remove and prune away those very inessential gates, and then we can fine-tune the later layers and to make sure the performance of the remaining parameters will satisfy our target task. Okay, so in terms of evaluation, we can still use some of previous tasks we used. For example, the classification task or the quantum chemistry task. And remember that we after our training our search process, we already have this trainable quantum layers at hand, and then we can just plug in this structure to the arbitrary task we want to use, right? So here we can have a look at the performance compared with others. So the first in red curve, that is the quantum knots search structure, and the second one is noise unaware search, which means during the search process we don't use any feedback from the actual device. So in that case, the search structure will be not having any feature or any like specialization for the actual device noise. And finally is the human design, which is the previous several state-of-the-art human expert design of the structure. So the first of all, a very obvious trend is that we still observe here is that when we increase the size of the circuit, we can firstly observe an increase of performance because of a larger learning capacity, and then after we further increase, say maybe many larger number of gates, because of the noise, we cannot get any benefits because noise will neutralize the larger learning capacity. But the important thing is that our search architecture has a better overall resilient to noise, because say we can afford a larger number of parameters because here we can see that the peak here is much larger than the human design peak. So in that case, using our circuit, we can better utilize the available capacity of the device. So say previously, say the physicists, they fabricate this device, and using some human design, you can only use like 40 gates. But using our search, you can better use the device by like adding to 60 or 70 gates. So using this system level optimization, you can better leverage the device. Instead of just waiting for the physicists to improve the device, we can use this search method to extract more computing power from the existing device. And also in terms of the quantum chemistry problem, which is finding the ground state energy for the hydrogen. So the ground state energy for hydrogen is actually the ground truth is minus 1.85, and this is the lower, the closer to the ground truth. So we can see also compare with the previous design, like the UCCSD, which is like a theoretical design, and also some noise unaware search random generated structure, and also the human design using our search structure will be much better than the previous baselines and closer to the hydrogen ground state energy. Okay, so we can see that in terms of the scalability, we can see whether our quantum knot structure can be scaled to larger device, right? So we can see like for the 10 classification task, for the previous all the other device, we can see a very close to 10% performance, which is basically random guess, because you already you have a 10 class and 10% is not learning anything. But for the using our search process, we can increase the performance on real device to like around 30%. Still not very high, but at least we are achieving a better like learning capacity like to the baseline design. And we think that using further noise mitigation, we can increase this noisy performance to higher percentage. And actually, for this number, if we're doing just noise-free simulation, we can achieve higher than 90% accuracy. So as large as 60% is already like degraded because of noise. Another interesting aspect is that say for the classical pruning, we don't expect that after the prune network, the performance will be the same or a little bit lower than the previous performance, because you are doing the pruning will reduce the capacity. But on the quantum here, the gate pruning actually can not only preserve performance but also increase performance by a little bit. So the rationale behind that is that, say, after you prune some inessential gate, so you retrain the remaining ones, the noiseless noise-free performance will be very similar, right? But because you remove those unessential gates, so the noise introduced is reduced, right? So in that case, that means that the impact from noise is reduced, so you can achieve better or closer performance to the noise-free simulation result. That means that's why the pruning, after pruning, our performance can even be increased by several percent here. Yeah, please. For this one, I think it's around like 30% of the gates. Yeah, that really depends on the like what kind of task. So during our process, we typically do a iterative pruning. Say first prune 10%, test the performance, and then prune 10%, and then you can see a curve like it's first going up and then going down, and you can find the best one, like best pruning percentage. Yeah. Okay, so another thing is that because we are using the weight sharing super circuit, so we expect that one can save us some search cost. So that's also a case that we show here. So basically, using this quantum knot search method, we can reduce the search cost if we are typically if we are search for say 10 class classification task, we can reduce by around 3 orders of magnitude of search cost. So during the search, we can see that we need to use this actual device as the feedback, right? So we evaluate that and then get feedback from actual device, and that one can be pretty slow sometimes because you need to submit a job and then you need to do the queuing. Sometimes queuing is crazy, like maybe you need to wait for several hours. In that case, we also propose whether we can use some ways to accelerate the evaluation. So the answer is yes. So we can use some data-driven method to construct a model that can provide us with very fast feedback. So for example, we can use some graph transform model to process the circuit information. So because the circuit can actually be represented as a control and dependence graph, right? So in that case, we can construct a data set where we can do this we can generate many of the random circuit, and then we find an efficient way, like concatenate of the inverse circuit, and then we can just evaluate this circuit by once to obtain the fidelity. So in that case, we can have a very large size of the circuit data set, and then we can use the graph transformer where we have multiple layers to do the processing of input random circuit structure. And then for different layers, we are using this attention layer to extract the information between one node to all the neighboring nodes, right? So in that case, after many layers here, and then we can obtain the final layer of the information of each node, and then we can have a global average pooling to do some average of all the features here, and then just adding a very simple FC head to generate the prediction fidelity. So we can do the training, data-driven training for all the parameters in the graph transformer according to our collected data set. So, and also some instead of using this graph neural nets to do the evaluation, we can also use some other representation. For example, some other paper, they are trying to use a very simple image to represent the state, right? So for example, if we have a swap case, we can have two pixels here to represent that. And also for some other case, we can use a single pixel or multiple ones. So in that case, we can also use the a graph representation or a matrix to represent the input structure. And also some other frameworks, they are not using the super circuit based, but they are using some reinforcement learning to do the search. That's also doable. So say the action is to increase the circuit structure one gate by one. So the R agent will place a quantum gate on a arbitrary or on a decided quantum bit qubits, and then the reward will be generated and returned to the R agent to gradually grow the structure for the circuit and finally reach a good point of the circuit structure. And also, of course, we can also use some differentiable search method where we can compute the gradients from the search structure and then use a gradient-based method to update the structure. There are some other works, for example, here also another circuit search structure work. We can see they are also using this super circuit setup, but the difference is that they are not the structure here. They are pretty constrained to this different kinds of structure, or where the quantum mass proposed method can be more like flexible. And also we can see that they are not using any of the real device feedback. So there are many to find a very shallow circuit, but it's not applicable to the target device. Okay, so I think we have a short break, and then we can go to the final section. We're going to introduce one final work that we can increase the parameter training fidelity. So previous several works, we introduced how can we how can we find the best structure on the actual device, right? So and then after that, actually, we can also make sure sometimes the training of the parameter can also be adapted to the noise. So say using parameter shift training or some other training steps, right? So before that, one quantum neural nets can be, I want to introduce one type of the quantum neural nets, which is a multi-node quantum neural nets. So that means, say, when we have an input image, and then we can encode this image to using some encoder, and after that we can apply these trainable layers, and then we can do the measurement to project that back to the classical values. So say we can do some measurement on the z basis, and then we can obtain the classical values. So the classical values here are represented as the double line here. So we can see the initial one is a double line, but we do some encoding for that, and after that, and after that we can encode this information to the quantum domain, and then use several quantum layers to do the processing. And finally, we can after this measurement, we return to the classical domain. So actually, we can do some processing in between. So you can add some post-processing, say some neural nets here maybe, or some noise mitigation techniques. So we are going to introduce several mitigations that we can apply in the middle of the classical domain. And then after that, we can encode this information back to the quantum block, and then do some other layers and do some final classification. So there is a trade-off between the whole process. So say because if we are accumulating too many layers, and then you can imagine that the noise is also very large, and maybe the final performance is not good because of noise. But if we do some cut of these layers using this classical measurement and then noise mitigation, we can make sure like the noise is reduced here and then reduced here, maybe several layers, but it's never a very deep circuit. And not very deep means it's not a large capacity. So there is a trade-off here. If you want to have higher capacity theoretically, and then you may be attacked by the noise of the deeper circuit. But if you want to have a more noise mitigation, then the capacity may be lost. So there should be some careful design of the number of blocks, and also what kind of mitigation here we want to use. So one one thing that we can typically apply to the middle layer of the mitigation is called the post-measurement normalization. So that means like after you measure this quantum state to back to the classical value, we can apply some normalization between the different result in the same batch, right? So say here the first keyword is that we need to do the normalization on the batch dimension, and another thing is that say we have a 4 qubits, and then say we have a 50 batch during the training for the classifier, and then we need to make sure that each of the value is the standard deviation and also the mean is computed on the batch dimension, not the qubit dimension. So say we just compute the mean and STD for this dimension, and then we can use the STD and mean to normalize the values on this dimension across the batch. So in that case, the normalized value will be more close to the noiseless result. So here we can show an intuitive plot. So say there are two colors. One is blue, which is noise-free simulation, right? Another is the real device distribution. So because the excitation is always from -1 to 1, so we can see for the noise-free simulation, we can have a distribution in blue. And then we can see that if we run this actual circuit on the actual device, there will be a severe distribution drift. So it's not the peak here is not aligned anymore, right? And the SNR here is also pretty low. And we can see if we do the normalization on both the noise-free version and also the real device version, we can see a match between the distribution of the yellow and also the distribution of blue. So that means we can drastically increase the SNR here from just 0.8 to over 5. So we have some theoretical proof here. So the basic idea is that after this, we can remove some of the coherent error impact to the measurement process, so that we can drastically reduce the noise impact. So here another thing is that we can during the training we can also do some noise injection. So say if the previous training on a pure classical simulator, then that's very different from the actual device because the actual the quantum simulator is not modeling any noise. So we can also inject some noise to do noise-aware training. So that's similar to the idea, say, for some other classical learning tasks, you can inject some noise. So here is also the case. For all the different noise, we can do some decomposition to the poly errors. So say if that's a very complicated unitary error, we can always decompose to the poly errors. And also we have the readout error. So with those values, and we can inject those errors to the actual quantum device during the training. So say for different device here, we have the information about what is the probability to have a X error here, and then we can insert this error to the actual device to mimic the impact of noise on the simulator. And also we have this measurement error after each of the measurement process to also make sure there is a match between the simulation and also actual device. And after this, because the real device is sometimes stochastic, so during the training, we are also doing the sampling of the errors. So maybe this is the first step. We sample these two errors, and next step, according to distribution, we sample another set of error. So during this process, we can make sure the parameters inside those parameterized gates can be fully aware of the real device noise and be more reliable. And here is an example for from the actual IBM's device. We can see after this SX gate, there will be 99.7%. That's no error, right? So that means, but you can imagine that the fidelity is around like 99.7%. But there are some other probability, like around 0.001 of the probability that there will be X error, and also the same probability for Y and Z error. And also here we have the real readout error matrix. So what is the usage of this? So the meaning of that is, so this one, the 0.98 on the diagonal is that, say, the ground truth is 0, and then there will be 98% of probability I measure at 0, but there is still like around like 2% of probability I measure actual 0 to 1. So that's the readout the error, right? So that's a non-negligible value because we can see this one is typically like 10 times larger than the single qubit error. So, but if according to the calibration of the system, if we know this value, we can actually apply this to the result, so we can mitigate this error because we already know what is the transition matrix, and then we can do a revert of that, and then make sure the readout error can be mitigated. So another thing is that we can do some quantization for the result. So for example, here we can see the result after measurement can be impacted by those noise. So say previously those are the values on the black circles here, and then because of some quantum error, there are some small drift, right? But after do the denoising via this quantization, we can project back them to the centroids. So that can be viewed as a denoising effect. But sometimes we can see if the error is too large, then we may push this to another wrong bucket, right? So in that case, during the training, we always want to make sure that the result measured from the actual device is very close to the centroids, because if it's very close, then a small error will not move this too far away from the correct centroids, and we can still be project back to the correct one. And in that case, we can add some loss function. We can have some loss term to the training process to always make sure like this is a quantized value and this is the original value, and we want to minimize this. So in that case, all the values can be very close to the centroids. Okay, so here we can have a look at the errors before and after quantization. So before the quantization, here we can see some of them is very large, maybe 1.1, and some of others have a small like 0.1 error. But after the measurement, quantization mitigation, we can see most of the errors are reduced to just 0. So that means the best we already removed the error. But sometimes for the large errors, they may have result in a different bucket. So in that case, our hope is that those values can be minimized, and the overall most of them can be corrected back to the original value. Okay, so in that case, we can have a look at the performance using this noise mitigation technique. So the actual evaluation framework we are using is the MNIST for classification, and also FMNIST here it means the fashion MNIST, like for some like shoes or some clothes, very similar to the a little bit complex than the handwriting digits, and also we have the vol classification, and also MNIST2, and also CIFAR classification. So we can see for the baseline result on the IBM San Diego. So San Diego is actually almost the best device at that time. So they have the lowest error rate, and we can see for the baseline it's around like 30%, and also for two classifications, 94% of the accuracy. And after this mitigation of the measurement outcomes, we can observe around like 10% of the boost of the fidelity. So say for MNIST4, we can increase from 30% to 40, right? And then after that, we can do the noise injection to make sure the training environment is very close to the actual noisy environment. And finally, we can do a quantization of the measurement outcome. So to make sure the most of the errors can be reduced to go projecting back to those centroids. So in that case, the final result here, we can see for the 4 classification, we can increase by over like 30%. And for this fashion amnesis, even larger. And for 2 classification, we can always achieve around like 94, 95% of the accuracy on the real quantum device. So that's pretty high and 10% higher than the baseline. And also that's also the case for the CIFAR and the fashion amnesis 2 classification. So here is a very interesting visualization that I want to share. So basically, here we are showing that there are 2 dimensions for this two class classification. So if the value here is lower than this blue dashed line, that means the result is actually classified as one class. So another is classified as another one. So that means this is the classification boundary, right? So say for the baseline, this one, we can see for all the different samples, each point here that is representing one sample, right? So say the stars means that that is the digit for 3, and for circle that is digit 6. And for this one, we can see they're all squeezed together because of noise, and all of them will be all classified to the same class, right? That means basically it's not doing any meaningful learning because you cannot do any classification. It's just a random guess. And then after this post measurement normalization, we can see the distribution is largely extracted, right, from this very small centered place to different points on the top, and also some points is on the bottom. So we can see for those green stars, they are already corrected, classified, and for those green circles, they also achieve higher correctness. And but we can see this place is still pretty small, and many of them are also squeezed on this boundary, right? So finally, after we inject this noise, we manually inject noise to make sure that the parameters can have a large separation boundary between those two classes. And we can see a further extraction to very top left corner, right, and also the very bottom right corner of the whole classification plane. And we can see sometimes it's still so most of the circles are corrected, classified correctly, because we can see maybe only one is not corrected. For the stars, most of them are still on the correct side, and some of them are not like misclassified, but it's much smaller compared with the previous two distributions. So that visually show the effectiveness of our several techniques. Okay, so in that case, I think that conclude our several steps of the training process. We introduced how to use TQ to construct the state preparation, how to construct the trainable circuit, and also do the training. And then we introduced the robust state preparation process and introduced the quantum NAS for the architecture search, along with several other works that perform the search, like using reinforcement learning or some differentiable search. And also we have this robust parameter training with this post measurement quantization, and also the noise injection, as long as the normalization. So yeah, I think that's all for the noise aware, like noise robust quantum machine learning. And I hope you enjoy this QML lectures. And yeah, so any questions? Questions? Yeah, please. Mhm. Yes. Mhm. Yeah, so that's so for the first question, so for a very large, very deep circuit, so especially for ML, we do have to separate that to multiple stages and do the mitigation in between, right? So another question is whether the compiler can search for that. So we do have some work that we try to find a good place to break the whole circuit, and also during this process, like the measurement of the state, you also have a design space, because you can do a large number of measurements to fully reconstruct the state. So like that's called like tomography of the original state. That is calling like exponentially number of measurement if you want to do a full state reconstruction. But there are some other ways, like say shadow tomography. So sometimes you don't have to pay that much cost. You only need to pay a very small subset, but you already cover the essential information from the state. Because for many dimensions, that's not very informative. You just need to measure those informative information out of the quantum state, and then do some processing mitigation, and then encode back. So I think, yeah, there are a large design space here, and very some interesting work try to reduce the cost. Yeah. Great question. Okay. So yeah, I think that's all for today. And next lecture we will have a presentation, final presentation. So yeah, good luck on the projects.